To go on, SCF-MO of polyatomic molecules. The hydrogen molecule. We model the electronic structure of the hydrogen molecule H2 by the addition of a second electron to the 1 sigma g orbital of the hydrogen molecule ion to give the configuration of 1 sigma g2. The orbital described is therefore psi plus of electron 1 times psi plus of electron 2. Of course, the 1 and 2 in parentheses are the location of electron 1 and 2 respectively. For the two wave functions psi 1, 2 as a product is an approximation that is valid only if the electron-electron interactions are ignored or replaced by some kind of average 1 electron potential energy, so that the true Hamiltonian operator can be written as shown on the next slide. The true Hamiltonian operator of the hydrogen molecule consists of 8 terms. The first and the second terms are electron kinetic energies of electron number 1 and number 2. The third and the fourth are interaction between electron 1 with nucleus A and nucleus B. The next two terms are interaction of electron number 2 with nucleus A and nucleus B. The next is electron-electron interaction. The last term is the nuclear-nuclear repulsion terms. If we use the H1 as the Hamiltonian operator of electron 1 as the sum of the kinetic terms and interaction terms, and H2 is the Hamiltonian operator of the electron 2. The terms of electron-electron interaction, we can get this value. Therefore, this term is ignored. The approximate Hamiltonian operator is therefore shown in equation 2.29. Is equal to the H1 or the Hamiltonian of electron 1 and electron 2 plus the nuclear repulsion term. Where each Hamiltonian I is expressed in terms of the coordinates of the electron ion alone. Instead of to get the wave function as the psi plus of electron 1 times psi plus of electron 2, we use the approximate wave function as shown in equation 2.30. Therefore, the wave function psi 1, 2 is equal to psi plus of electron 1 times psi plus of electron 2 and multiply with the factor sigma 1, 2. This factor sigma 1, 2 is the spin contribution as shown in the equation below. The expression based on the Hamiltonian operator and approximate wave function of the hydrogen molecule as mentioned on the previous slide. The molecular potential energy curves can be obtained as shown in figure 2.6. It has a minimum at R or bond length equal to 1.4 bond radius or equal to 74 picometer, and the minimum lie at the energy of 0.77 Rydberg or equal to 350 kilojoule per mole. This value is below the value of 2 times the energy of the 1s orbital. This means the energy of 2 separated hydrogen atoms. The experimental value are 1.4 bond radius and the energy of 0.33 Rydberg or equal to 430 kilojoule per mole. For the bond length or bond length obtained from the calculation obtained from to solve the Schrödinger equation using the Hamiltonian and approximate wave function. Result, the value is in good agreement with the experiment. But for the energy are quite different. For the improvement that can be made includes the use of a more flexible basis set, the use of SCF procedure, and the incorporation of the electron correlation. This slide just shows you the conversion of the units of energy and bond length. For 1 Rydberg is equal to 13.6 electron volt or equal to 1312 kilojoule per mole. And for the length, 1 picometer is equal to 1 times 10 power minus 12 meter. And A0 or bond radius sometimes we call atomic length unit, is equal to 0.529 angstrom. Diatomic molecule. There are two types of the diatomic molecule. One is the heteronuclear, and the second one is the homonuclear. The hydrogen molecule and nitrogen gas, oxygen gas are homonuclear diatomic molecules. From the hydrogen molecule to the LCAO-MO description of as homonuclear diatomic molecules. The basic principle for the construction of the molecular orbitals is to form the linear combinations of atomic orbitals that have the same symmetry with respect to the rotations about the internuclear axis. The internuclear axis we call the principal axis. More formally, we build linear combinations of atomic orbitals that have the same symmetry species within the molecular point group. We have stressed that good theory provides techniques for selecting atomic orbitals that may contribute to bonding, but other types of arguments must be used to decide whether these orbitals do in fact contribute, and to what extent. There are essentially two criteria in this connection. The first, to participate significantly in bond formation. Atomic orbitals must be neither too diffuse nor too compact. In this case, there would be only weak constructive or destructive overlap between neighboring atoms, and only weak bonds would result. It follows that in the period 2 of the periodic table, the overlap between 1s and 1s orbital can be largely neglected in comparison with the overlap between 2s and 2s orbital. For 1s orbitals are too compact to have significant overlap with each other. Indeed, it is generally safe for qualitative discussion at least to consider only overlap between orbitals of the valence shell, for only these orbitals are neither too compact nor too diffuse to have significant overlap. The second criterion, the energy of the orbital should be similar. To see why this is so, consider the following secular determinant. for the bond formed between two different atoms A and B. The secular determinant shown in equation 2.31. The solution. The roots are found by solving the quadratic equation for the energy, and when the value of the alpha B minus alpha A is much more larger than the value of beta, and S equals 0. Therefore, the energy E plus is equal to the alpha A minus B square over alpha B minus alpha A. E minus is equal to alpha B plus B square over alpha B minus alpha A, where alpha and beta are the molecular Coulomb integral and the resonance integral, respectively. These results, which are shown in figure 2.7, show that the molecular orbital energies are shifted from the atomic orbital energies alpha A and alpha B by only a small amount when alpha A and alpha B are very different. The implication is that in the homonuclear diatomic molecules, the atomic orbitals of the identical energy dominate the bonding. The strongest bonds will therefore have compositions such as 2s and 2s orbitals and 2p and 2p orbitals. And there is no need to consider 2s and 1s and 2p and 1s contributions. There is normally insufficient energy difference between 2s and 2p orbitals for it to be safe to ignore 2s and 2p contributions, although in elementary accounts that is often adopted as an initial approximation. The figure 2.7 shows the molecular orbital energy levels stemming from atomic orbital of the same energy as shown in the top picture, and different energy for the bottom picture. The top one is the homonuclear diatomic molecule. For example, hydrogen, nitrogen, and oxygen gases, which are uniform. The lower image belongs to the heteronuclear diatomic molecule, such as carbon monoxide and nitric oxide, which are non-uniform. The heteronuclear diatomic molecules. The qualitative effect of the presence of two different atoms in a molecule is for there to be a non-uniform distribution of electron density. specifically for molecular orbitals of the form as shown in equation 2.23. It will no longer be true that the value of the absolute Ca square equal to absolute Cb square. But if atom A is more electronegativity atoms of the two, then the bonding combination will have the value of the absolute square of the Ca much larger than the value of the absolute square of the Cb, with Ca and Cb of the same sign, as it is a contribution to the lowering of energies for the electron to be found predominantly on the atom A. As compared with the bonding combination, on the other hand, for the anti-bonding combination, of course, the absolute square of Ca larger than absolute square of Cb, with Ca and Cb of opposite sign, and an electron in this orbital will be found dominantly on the atom B. Its occupation of an orbital on B is a contribution to the lessing of the energy of this molecular orbital. The symmetry adapted linear combinations. The molecular orbitals of polyatomic species are LCAOs, just like those in equation 2.17, which we repeat here as the linear combination of atomic orbital equations shown below. Psi is equal to the summation R, which is the orbital number of the Cr multiplied with the orbital R. The main difference is that now the sum extends over all the atomic orbitals of the atoms in the molecule. However, as for diatomic molecules, only atomic orbitals that have the appropriate symmetry make a contribution, because only they have net overlap with one another. When a molecule lacks any symmetry elements, there is no way of avoiding assembling its molecular orbital from the entire basis set. However, when the molecule has elements of symmetry, the group theory can be particularly helpful in deciding which orbitals can contribute to its molecular orbital, and in classifying the resulting orbitals according to their symmetry species. This symmetry adapted linear combination appreciation. The concept behind the construction of symmetry adapted linear combination, which is denoted by SALC, is to identify two or more equivalent atoms in molecule, such as the two hydrogen atoms in water molecule, and to form linear combinations of the atomic orbitals they provide that belong to specific symmetry species. To consider the water molecule, which belongs to the point group C2V, if we use the six-member basis, namely H1SA, H1SB, O2S, O2P, O2PY, and O2PC, then we should expect a 6 times 6 determinant and a 6th order equation to solve for energies. The figure 2.8 shows the symmetry classification of the oxygen atomic orbitals in water molecule and show C2V molecule of the waters, and the two symmetry adapted linear combinations of the H1s orbitals. This side A1, this side B2, and the side B1 are molecular orbitals. They are a combination of the atomic orbitals for the oxygen, but for the hydrogen is the symmetry adapted linear combination are used. It should be clear from the figure 2.8 that the two linear combinations based on the symmetry adapted linear combination are shown as the equation 2.35. This can have net overlap with O2S and O2PC with O2PY, but not with O2PA. This observation suggests that the molecular orbitals in water will fall into the following group. For the molecular wave function shown in the equation 2.36, psi A1 equal to linear combination of Ci times 3 O to S orbital plus C2 times 3 O to PC orbital and plus C3 of the symmetry adapted linear combination as A1. And the third and the last equation, psi B2 is equal to C4 times 3 O2S orbital plus C5 times 3 B2 which is the symmetry adapted linear combination. Of course, we take C as the two-fold rotation axis and X as perpendicular to the molecular plane. MO models. There are series of molecular orbital calculations of showing the electronic structures of the polyatomic molecules, such as the molecular orbital calculation on conjugated pi system, such as aromatic compound, organic compounds. The MO calculations are obtained using the Ruggell approximation or the Ruggell method. For the compound or the complex for the inorganic chemists, these compounds are calculated for their energy and geometry. They use the ligand field theory as the MO calculations. For the MO calculations on solids, using the band theory of solids, such as the tight binding approximation or the Koenig-Penny models. The calculation of electronic structures. Solution of the electronic Schrödinger equation with the Born-Oppenheimer equation is employ the equation 2.40. The Schrödinger equation H Hamiltonian operator operates on the wave function as a function of the location of electron and nuclei. As the location of the nuclei are fixed, the electronic wave function psi therefore depends on the electronic coordinates r, small r, and parametrically on the locations of nuclei, capital R. E capital R is the electronic energy. The Hamiltonian is shown in the equation 2.41. The first term of the Hamiltonian is the kinetic energy of the electron in molecule. The next term is the interaction between electron and nucleus. The last term is the electron-electron interaction. To calculate the electronic structure, the Hartree-Fock approach is employed. Each electron is considered to be moving in the electrostatic field of the nuclei. and the average field of the answer n-1 electrons. The spin orbitals that give the best n electrons determinantal wave functions are found by using the variation theory or the variation principle method, which involves minimizing the Rayleigh ratio, as shown in the equation 2.42. The electronic energy is equal to the integration of the psi h psi dx divided by the integration of psi star times psi dx. The Lutan equations. This expression is one in a set of m simultaneous equations, one for each value of I, that are known as the Lutan equations. The entire set of equations can be written as the single metric equation as equation 2.43, where C is an m times m matrix composed of elements C, I, J. E is an m times m diagonal matrix of the orbital energy E, A. S is an overlap metric, and F is Fock metric with the elements F, I, J. The Fock elements can be computed from equation 2.44. Fij equal to the integration over the position R1 of psi I star of electron 1 F1 psi j of electron 1, where F1 is the Fock operator expressed in terms of the spatial wave functions. The spatial function psi A1 occupied by electron 1, and write it in the notation of as follows, as shown in equation 2.45. Fock operator acting on the psi A1 equal to the energy A psi A1. Lutan's equation have a non-trivial solution only if the following circular equation is satisfied. Determinants of F minus EAS equal to 0, as shown in equation 246. This equation cannot be solved directly because the metric elements Fij involve integral over the Coulomb and exchange operators, which themselves depend on the spatial wave functions. Therefore, as before, we must adopt a self-consistent field approach, obtaining in each iteration a new set of coefficients Cji, and continuing until a convergence criterion has been reached, where coefficients Cij are in LCAO-MO equation, as shown in equation 2.47. The wave function psi A equal to summation from J to M of Cji of the function J. Phi J function is fixed linear combination of the original or primitive Gaussian function G centered on the same atomic nucleus. Phi J can be obtained using the equation 248. Is equal to the summation of I of the dji gi. This basis is called as the GTO or Gaussian type orbital basis set. The Orbitals versus Semi-Empirical calculations. There are two main approaches to the solution of the Schrödinger equation. In an Orbitals calculation, a model is chosen for the electronic wave function and equation 2.40 is solved, using as input only the value of the fundamental constants and the atomic numbers of the nuclei. The accuracy of this approach is determined primarily by the model chosen for the wave functions. For the large molecules, accurate Orbitals calculations are computationally expensive, and semi-empirical methods have been developed to teach a wider variety of the chemical species. A semi-empirical method makes use of a simplified form of the Hamiltonian and stable parameters obtained from the experimental data. In both cases, it is a challenging task to compute chemically accurate energy. That is, energy calculated within about 0.05 electron volt, or about 5 kJ per mole of the exact value.